Okay, today we're going to be working on proving trigonometric identities. Here's a big list of trig identities for you right here. An identity in math is an equation that is always true for all the values where the expressions are defined. For example, a squared plus b squared is always equal to c squared in a right triangle. And a times the quantity x plus y is always equal to ax plus ay. These are a couple of identities. Now, you may have stumbled across a couple of our trig identities when we were graphing. For example, sine of x is equal to cosine of x minus pi halves. You know that if I take the cosine curve and move it to the right pi halves, I'm always going to get the sine curve. You also may have noticed that a sine curve with a horizontal reflection will get you the exact same thing as a sine curve with a vertical reflection. That particular identity there is called one of our odd-even identities, and that's because sine curve is an odd function. That's something you're going to learn about later probably in your math careers. Now, there are a gazillion of these trig identities. Okay, for this course, we're only going to need the ones highlighted here and surrounded in purple. Okay, we have the reciprocal trig identities, which are really more like definitions. We have the Pythagorean identities, and we have the quotient identities. So let's take a couple of these identities and prove that they're always true. Okay, let's have a look at this one. Sine squared theta plus cos squared theta equal 1. Oh, we haven't talked about sine squared theta. Okay, sine squared theta means the same thing as sine of theta all squared. Sir, that seems kind of silly. Why do they write it that way? Well, I think the main reason they write it that way, because if I said sine of theta squared, you wouldn't know whether I was talking about that one or that one. So I guess somehow this makes it less complicated. So we're going to write it as sine squared theta when we mean sine of theta all squared. Okay, now back to the proof. All right, sine squared. So we're going to set this up as a left side, right side proof. So left side is sine squared theta plus cos squared theta, and the right side is equal to 1. And I'm trying to get my left side to look like my right side. What I'm going to start with here is I'm going to start with a triangle. And I'm going to label that triangle with an angle theta, and I'll call that x because it's horizontal, and that y because it's vertical, and we'll call that r. Now, I could probably have just used a, b, and c like we did in the Pythagorean theorem a second ago. A squared plus b squared is c squared. But what we're going to do is we're going to use those because it's a bit more like the unit circle. Now, knowing that, I can look at my left side here. Sine of theta is going to be opposite over hypotenuse, and that is going to be squared. Right side is going to be adjacent over hypotenuse, and that's going to be squared. And I'm going to get here, and I'm going to end up with y squared over r squared plus x squared over r squared. And now I need that to be equal to 1. One of the great things about proofs is you know what you're supposed to end up with. You could almost fake your way through this. You know that this has got to be equal to 1. So the only way that's going to be equal to 1 is if that numerator is also r squared, and then your numerator and denominator will be the same. So you could just throw an r squared on there, and then r squared over r squared is equal to 1. And then you could say, all right, left side equal right side, and I'm done. Now, obviously, faking your way through it is not good practice. My point is, hopefully, what's going to happen is you're going to realize the only way this could possibly work, and we're not going to ask you to prove something that's not true. The only way this could possibly be equal to 1 is if the x squared plus the y squared is equal to the r squared. And so what hopefully would happen then is you would look over at your triangle, and you would go, oh, of course, x squared plus y squared is equal to r squared, and then you'd put your r squared in, and r squared over r squared is 1. And this is, of course, in case you somehow missed that it's called the Pythagorean identity. Okay, let's prove one of these quotient identities. is always true. Tangent theta is equal to sine theta over cos theta. Okay, I'm going to look at my left side is equal to tangent theta. My right side is equal to sine theta over cosine theta. This time I'm going to work with the right side a little bit. I'm going to again draw a triangle. And that's theta. And that'll be x, y, and r again. So the right side, sine of theta, is opposite over hypotenuse. So that's going to be y over r. Cosine of theta is going to be adjacent over hypotenuse, which is x over r. Multiplying top and bottom by r, because r is not 0, we end up with y over x, which is, of course, the ratio of the opposite side to the adjacent side. So that makes this equal to tangent of theta. So left side is equal to right side, therefore tangent theta is equal to sine theta over cosine theta. Let's take a look at the other one. Okay, cotangent theta is equal to cosine theta over sine theta. Left side is again, let's see, cotan theta. Right side is cosine theta over sine theta. Now I'm sure you guys can see that if we set this up and did our triangles, this would fall into place exactly like the last one did. But we're going to do this one a little different this time. We're going to start with the left side. Cotangent is theta. I know from my reciprocal trig identities that cotan theta is the same thing as 1 over tangent theta. And I know that tangent theta is equal to sine theta over cos theta, which we just proved. Okay, and I know that 1 over that, in other words, the reciprocal of sine over cosine, is equal to cosine theta over sine theta. And once again, my left side is equal to my right side. So I'm done, and I didn't have to go by way of the triangle that time. So once we start accumulating some of these trig identities, we're going to start using those instead of going the route of the triangle. So now we have a good list of about 11 trig identities. So what are we going to do with these trig identities? We're going to use them to prove other trig identities. Oh, the fun we're going to have. Fasten your seatbelts.